Let's talk about the order of growth notations here. We talked a lot about fundamental operations and how we count the constant time operations together inside a function. Let's say a function or algorithms performing with n elements may require 2n squared plus 4n plus 3 comparisons. There's got to be a way we could express the efficiency of this algorithms involving these many comparisons. So this is where the order of growth notation comes in. This is what we call big O notation, which is a mathematical way of describing how a function generally behaves in relation to the input size. The input size is n. The number of comparison is expressed in terms of n, in this case, 2n squared, 4n, 3. Generally, when we have something like this, we can eliminate constants or operations that are relatively small compared to the total size of comparisons we're talking about. If you chart this, x, y, this is y, this is x, or in this case, this is n, it's probably going to go up like this, right? The impact of this 3, which is slope, is really, really small. So is 4n. They're pretty small. So is 2, but the impact in terms of the exponential growth required in this equation here is the n squared. We use O of n squared. So big O, like I said, this is a notation. There's upper bound, lower bound. From a mathematical standpoint, when we are talking about order of growth, we take the most significant variable in the equations, n squared, as the worst case, which is the big O notation. Given a function that describes the running time of an algorithm, this big O can be determined using such rules. Let's say if you have an equation that's 2n squared, 13n plus 2. In order to measure the big O, or the order of growth, you take this and put a big O next to it. What is really important is, let's say if this equation is the summation of several terms, the highest order term is kept and the other one discarded. The highest order term is this, which means this could be discarded. Now you're ending up with a 2n squared. That's rule number 1. We do a transformation. The rule number 2 is if this equation 2n squared has a term that is a product of several factors, all of the constants are omitted. 2 is a constant, so it's omitted. So we ended up with O of n squared. That's generally the rules when figuring out the final order of growth with respect to an algorithms that require this many comparisons. Let's move forward to the next slide. This is an example. One of the most fundamental sorting brute force sorts that exist. Basically, this sorting algorithms allows you to sort a list of alphanumeric strings in the alphabetical order or in a natural string order, so to speak. Or you can have an integer array sorting all of the elements or the integers by their ascending order or descending order. That's what we meant by sorting, to place them in some sort of order. And selection sort is just one of the methods to do so. We won't get into the improvement, the specific algorithms itself. This is a pictorial representation of it. Later on, we're going to go through these in details, so on and so forth. Just look at the selection sort code. For example, this one. The selection sort starts right here. This is the entry point. This for loop calls the swap. This swap has a min index. This min index has a for loop. What is this for loop? You have an array with the beginning index. This is the beginning part, and this is the end index. You can have n number of iterations in this for loop. This for loop also comes with n index. This is worst case n index. Let's say some of the elements in the selection sort, most of them are already sorted, then this will be done pretty quickly. Worst case is you've got this for loop, which calls another function that has this for loop in there. This is a nested for loop saying this n number of case. Inside another for loop, there's another one that says there's n number of them. So this is n squared. If you express this the order of growth, this will be big O of n squared. We're talking about worst case scenarios here. We don't really care about this basic operations. Consider it really small. This is O of 1. This one is O of 1 too. O of 1. Because the second part is all nested, this is technically n times O of 1 because there is going to be n number of assignments, given this entire mean index is sitting inside these other functions. For estimations, we also go with the simplifications. The order growth is O of n squared in this case. Let's look at several others. We've got several different types of orders of growth, and it's very common to have O of 1. This is basically constant, like x equals 2 is O of 1. O of 1 means there is a bounded time and the amount of work is not dependent on the size of the problem. So let's say the size of the problem for the Bob Ellis guessing game is 1000, is n. X equals 2 is not dependent on any other variables. There is not a variable length associated with this. O of log n, this is called logarithmic time. Let's just say you have binary search. Binary search, also O of log n. N is the number of elements inside the array. O of n is called linear time because this goes up like this. N log n is the order of growth for the most efficient algorithms for sorting. Quick sort, merge sort, and heap sorts are O of n log n, natural log. O of n squared is called quadratic time, and then there's an exponential time, 2 to the n. This is extremely slow. So these are the common order of magnitude. Let's see if we can illustrate these different orders in terms of the numbers. You can see comparisons here. In comparisons, exponential is the worst one, 2 to the n. Another worst one is what we call factorial. If you have in this is probably the worst. Wouldn't want to have something like this. This is cutting the problem space n into logarithmic natural log space. Growth is pretty slow in terms of time and space. N log n is the second fastest, and then when you get into n squared and cube, this is typically frowned upon. You wouldn't want to have n squared. Technically, the best one is O of 1. This takes no time. This is the comparison of growth rate. There is another slide. It says the way to simplify analysis of the algorithm, consider worst case. The average case, theta. Big O is the worst case. We have omega. This one is the best case. This is not a math class. This is not operational research. Just focus on the worst case, big O. This is pronounced big O. Count the fundamental operations. Consider worst case. So this is big O. And make sure that it is the most used operation. We can eliminate, let's say 2n squared plus 4n plus 2. The most used operation is this, because this is n squared and it's much, much bigger and higher growth than the other terms. You can estimate the growth complexity from there. This is it. Generally, the order of growth complexity analysis applies to large problems. This means when n is much larger than 0. N could be 1 million, could be several billion, petamillion large. Let's say if you have iteration that goes through only 10 iterations, that's not large. Generally, we use big O for very large problems. We measure the complexity of analysis in terms of the big O for time and space.